So let's look at the difference of the curve to start off with. So here we have the strong acid and the strong base, and here we have a weak acid and a strong base. One thing you may notice right off is that the equivalence point has a different pH. So strong acid and strong base, again, mix. You form a salt that's neutral, pH 7. But if you're titrating a weak acid and a strong base, the conjugate of the strong base will be ineffective, but the conjugate of the weak acid will act as a base. So the pH then at the equivalence point, when you've added equal number of moles of your strong base as you had weak acid, then you'll have the conjugate base around, and the pH will be greater than 7. So in working the problems, if you get an answer with this type of titration problem that's different than that for pH at the equivalence point, you're going to know that you did something wrong. You need to go back and check your math. Another big difference has to do with the curve shape down here. And so you notice a difference over here than over there. And in a titration that involves a weak acid and a strong base, you have a part of the curve that's known as a buffering region. And the pH is fairly flat in this buffering region, as shown down here. So that's in contrast. There's no such buffering region on this side. So here the pH will go up, it'll level off, and then go up again. And this, for some of you, is probably the frustration in doing acid-base titrations in lab, because you're adding and nothing's happening and nothing's happening and nothing's happening, and you're in this region, then all of a sudden you add just a little more and whoop, you're up here. So notice how steep that is over here. So you can, sometimes when you're in the buffering region, it seems like you're never going to reach the end of the titration, and then it'll happen all too quickly. So buffering region, remember, a buffer is something that has a conjugate weak acid and weak base pair, and that in a buffering region, the pH is pretty much stays fairly constant in that region. It acts as a buffer, neutralizing the pH, maintaining the pH by being a source or sink of protons. And so here, the pH then is staying constant in that buffering region. So those are some of the differences between the type of curves. Another point that I will mention, or term I will mention, that has to do with weak acid and strong base, or a weak base and strong acid, is this half equivalence point concept. So a half equivalence point, you've added half of the amount of strong base that you need to get to the equivalence point, and that's right in the middle of that buffering region. So that's another point where you'll be asked to calculate the pH. So now let's look at different points in a titration. So first, let's walk through and just think about what is happening. So when we start in this titration of a weak acid and a strong base, before we've added any of the strong base, all we have is a weak acid. So it is a weak acid and water type problem. And so here I've drawn our acid, and the acid has its proton, which is going to give up when you start doing the titration. So that's what we have at 0 volume. Then we start adding our strong base. And the strong base is going to react with the acid. One-to-one stoichiometry, it's a strong base. It will pull off it'll pull off protons off the same number of moles of the strong acid as the number of moles of the strong base that were added. And so then you'll start to have a mixture of your conjugates, your weak acid and your conjugate base. So the base is A- here. And so if you have a mixture of a weak acid and its conjugate base, that's a buffer. And so you'll move into the buffering region here. So that's at any volume that is greater than 0 and less than the equivalence point is going to be around in that region. Then we have a special category of the buffering region, which is when you've added the volume to get to the half equivalence point. And when you've done that, you will have converted half of the weak acid to its conjugate base. So you'll have equal number of moles of your weak acid as moles of the conjugate base. Half has been converted. And so that's a special category right there. Then you get to the equivalence point. At the equivalence point, you've added the same number of moles of strong base as the number of moles of weak acid you have. So you've converted all of your weak acid to its conjugate base. So all you have is conjugate base now, and so that's controlling the pH, so the pH should be greater than 7. So that's a weak base in water problem. And if you keep going, then you're going to end up with a strong base in water problem. The weak base will still be around, but it'll be negligibly affecting the pH compared to the fact that you're dumping strong acid into your titration. And so that's this part of the curve. So you see that in one type of problem, one titration problem, you actually have a lot of sub-problems or subtypes of problems. You'll have weak acid, buffer, special category of buffer, a conjugate base or a salt issue, and then a strong base. And this is one of the things that people have trouble with in the titrations, because we may not ask you to do all the points. We may just sort of jump in somewhere and say, OK, what is the pH at the equivalence point? And you need to think about what's happened to get to the equivalence point. Or we may jump in and ask you about a region that would be in the buffering region. And you have to remember that at that point, you should have some of the weak acid and also some of the conjugate bases being formed. So it seems like there are a lot of different things, but there are only 5 types of problems. But in a titration curve, you run into a lot of those different types at different points in the problem.